So welcome everybody for the third in the set of lectures. One organizational announcement is that next week, because of organizational reasons, that's because we have interviews at IISc. There might be some readjustment in the timing, so I will confirm that once the schedule of these interviews become clearer. But Shamik, please take it from here.
Okay, thanks. So I'll now talk about this. Last time we talked about these operators, these conformal primaries. We introduced these two kinds of objects. Sigma, and then we also introduced basically the three-dimensional field, which can be thought of as a Heisenberg picture field. So okay. So then we said that this is basically, you can think of these objects as defining some sort of free field on Scri plus. And now actually I want to point out one important thing, that this free theory, which is basically defined on Scri plus. So the thing that we emphasized was that given this Fock space, I mean, which is constructed out of this creation annihilation operator AP sigma and A dagger P sigma, okay. So from there you can actually construct two types of field. One field is these fields, these phi's, which this phi epsilon h bar and u z z bar, which live on the Scri plus. And then the other kind of fields are the space-time fields. Okay, so those objects, I mean, suppose if I just talk about the scalar field, so sigma equal to 0, then those we know are of this form. So those both are like free fields, but yeah. Okay, so this is the massless field. So this is a space-time. Okay, so this is defined on the space-time. Okay, whereas this field, this phi field, phi u z z bar, so that object is defined on Scri plus. So now actually what the basic object, since it's a free theory, so it has this it has this standard, this Fock space commutator like AP sigma and A dagger P prime sigma prime. So you can write it as delta sigma sigma prime. Okay. So now using this, one can compute the 2-point function. Okay, so that 2-point function is on Scri plus. Suppose this is an outgoing field. So this is an outgoing field. So we can write it as some u z z bar and phi of epsilon -1. So h prime bar prime located at some other point u prime z bar prime. Okay, so this is essentially the vacuum expectation value of these two fields, and this is essentially the transition amplitude for a massless particle on Scri plus to go from u prime z bar prime to u z z bar. And this can be easily computed from using this thing, using this object, the basic commutator between a dagger. And this, if you do the calculation, what you will get is this. So this is the gamma function, and okay. Okay, so this is the result of this computation. So you have this gamma function, and the important, basically, the important object that I want to emphasize is this delta function. Okay, so basically, this 2-point function. So this shows that if you think of the so you have this three-dimensional space. Okay, suppose so if you think of the zz bar as sort of the spatial coordinates, the space like, and u as the time in this three-dimensional space, then this object is actually shows that this is ultra local because of this delta function, delta 2 of z prime minus z. So if you just think of, if I draw this, so this is like a cylinder. So this is the u direction, and this is like z and z bar. So the way particles move is like this. So they sit at one point. So, mm, so they sit at one point and they just move like this. So they don't move in the z direction, zz bar direction. So they are just moving in the u direction. So they just don't move actually. So you don't have any, so particles don't move in the spatial direction. Okay. Now this is actually very different from the space-time A, because we know that in space-time, if you have 2 points xt and x prime t prime, particles can move between these 2 points. You don't have any constraint like say delta prime of x minus x prime. So you don't have any constraint like this. Okay. Now, so what is the consequence of this thing, that this ultra locality on Scri plus is that if you look at this 2-point function, okay, so if you look at this 2-point function, so we know that this has the standard. Okay, so this 2-point function, of course, has the Poincare invariance. I mean, that is built in. So this, of course, is Poincare invariant. So that is built in. But then you can see that you have some sort of an emergent symmetry on Scri plus, and that symmetry has a form where you can shift u going to u plus some function of z bar, and z bar remains unchanged. Okay, where if z bar, so this is an arbitrary function on the plane. Okay. Now we know that the, if I just talk about the global space-time translation, so for, okay, so let me just okay. So for global space-time translation that we discussed last time, how does u shift? U goes to u plus some constant plus some say b times z, b bar z bar plus some c z z bar. Okay, and then z goes to z and z bar goes to Z bar. Okay, but now you can see that this also has this additional, this emergent kind of symmetry because of this delta function. This you have this delta 2 of Z prime minus Z, and so you can shift u not just by this function a plus bz plus b bar z bar plus c z z bar, but by any function of z and z bar. Okay, so in particular you can have an arbitrary shift, for example, like of the form where like u goes to u plus some delta, I mean delta is some small number, okay, times say some z to the power n plus 1, z bar to the power n plus 1, where m n they're integers. Okay, and so similarly you don't change z and z bar. Okay, now these you can call super translations. So this is an infinite dimensional symmetry of this free theory on scry plus, and it is there because of this ultra locality. Okay, so this is basically the first hint that if you have a theory on scry plus, so this is basically the first hint that if you have a theory on scry plus, then it may have infinite symmetries, infinite global symmetries. So that is important. Okay.
Shamik, I had a basic question. So
Yeah.
you are reaching this conclusion by looking at the 2-point correlation function between phi's, the two phi's.
Right. Right.
But if it is a true symmetry, then it should be a property of any point correlation function. Is that obvious that it follows from?
But the thing, yeah. So right. So in this case, since it's free, so any point can be expressed in terms of.
Okay.
Yeah. So now actually I will talk about the interacting case where we will actually consider an n point function. Yeah. But this is basically, you can think of this as some kind of motivation for the this is kind of the first hint that you can have these infinite dimensional symmetries on scribbles, and you can just see it in this way. So this symmetry is not clearly visible if you work with fields defined in the bulk of in the 4-dimensional spacetime. Okay, so this is actually a good thing about this free theory on scry plus. So yeah, so this is basically the first that, well, I mean it's kind of saying that the this is kind of holographic, that if you look at them from scry plus, then things actually become more symmetric in this sense. Okay. Okay, so this was for the free theory, and so now, well, so this actually, if you want to say, in fact, the point is that you can consider a charged scalar field, and then you can get the infinite number of U1 symmetries on Scri plus. So this was actually discussed in this paper. So if you want to know, like you can construct the charges and all these things. So uh, okay, so I just gave you just brief uh, introduction to that actually. Yeah, so now let's talk about the interacting case. So symmetries.
Hi, Samikda.
Yeah,
Uh, so I was just trying to understand in this realization that there is this symmetry emerging out. Uh,
right.
is it possible to understand from the geometry point of view that this Scri plus is some kind of a null surface? Has that input gone in or?
Well, so that input, because this construction, we have not used the bulk space-time. In fact, the point is that this U, Z, Z bar, so I am just calling it U because, well, because it transforms like U if I apply this SL2C and the global space-time translations. But otherwise, we have not used any kind of bulk information, because you can see that for example, if you look at this, so I mean this AP, so the Fock space, so that can be constructed, you can construct it without a reference, in a sense, without any reference to the bulk space time. Okay.
Okay.
And then once you have that, so once you have the A daggers, you can construct these fields, these phi U Z Z bar, and then the rest of the things, they don't require any kind of information, because this 2-point function of phi and phi prime, say, so that just follows from this. Okay.
So will it be justified to make this statement that if I have a null sheet or null surface and I want to construct a free scalar field theory on that, this symmetry will still be there?
Well, that is for an arbitrary null surface. Well, so on the null surface, that information has not really gone into this because there is no metric so far. Okay. So here you can say that you have a space, just a space U Z Z bar. Okay, and I know how this SL, so how the Poincaré group is acting on that.
Okay.
And I have a bunch of fields actually on that, and that's all we need.
Okay.
So the point is that the null surface, because that itself of course will require an introduction of a metric, but that we don't need actually for this on-off structure. But then the point is that once you look at it from the point of view of the space-time, then you can realize that this must be the Scri plus, because this U, Z, Z bar, they are transforming in the same way as the boundary coordinates of the Minkowski space.
Nice.
So that is essentially the point. So far we have not really introduced any kind of metric. So null surface as such, is that concept is not well defined here. So we have just the quantum mechanical laws and some abstract space on which this Poincaré group can act. So that is all we need actually. Yeah. So is that?
Hello, I have an IB question.
Yeah. Please.
So does this fields, I mean, phi u ZZ bar also transform as primaries under the super translations as well?
Well, primaries of super trans, yeah. So the point is that these are free fields. Okay, so they are not, well, primary. Well, since it's a translation, so you cannot. Well, so you have to define what you mean by primary. But the point is that under SL2C it does. Okay, so that is the transformation law, which you wrote down like this: phi epsilon H bar use
Right.
the bar, and this goes to some phi prime. It's like the standard.
So these are I mean these are like these transform covariantly, right? With weight
Yeah,
H and
yeah,
H bar.
exactly.
But
So basically, but so for the time being, let's just talk about the free fields. Okay, so now we'll go to the interacting case. Yeah.
okay, okay.
Okay. So the reason I said that this is actually an kind of emergent symmetry, because we did not start with this, right? So then we constructed this 2-point function, and then we found that okay, since this 2-point function, since this 2-point function is ultra local, so I mean it looks like this. So you don't really move in the direction of ZZ bar. So you just move in the U direction. So this 2-point function will not change if I shift U and U prime by any function of Z and Z bar. So that's how we got this.
Right. So the symmetries are there at the level of correlation functions.
Yeah, yeah.
That's for sure.
So that's why I said that it's kind of an emergent. Yeah, actually.
Okay, okay. Thank you.
Yeah, yeah,
Question.
yeah.
Hi. Hello. Okay.
Yeah,
So
please go ahead.
this holographic thing. I mean, like, you said that you are some in which there is no metric present, right? If I am
Yeah, so
not wrong.
far, so
Like,
these
irrespective of any metric.
yeah, so your voice is breaking. I mean,
Hello.
yeah,
Okay.
yeah,
Okay.
I
Sorry.
can't actually
Hello.
hear you clearly.
Okay. At the original formalism of this BMS symmetry case, which
No, see,
actually uses this metric with formal
no, no,
metric.
no, wait. So first of all, we cannot really talk about the BMS here. Okay. So what I have done, so BMS, of course,
Okay.
will require dynamical metric or dynamical
Yeah.
graphic.
The
But it
leading
is
order
not
one over
a,
our
so
correction
this
corresponds
is,
to this.
no, what?
So this in the BMS formalism, the super translation comes from the leading order corrections of one over r corrections to the metric, right?
Yeah, yeah. But those things are not there
Hello.
now.
Yeah, but I was on holographic. I mean, what you told holographic, because I understood that this is
Actually,
only
your voice
sky
is
plus, which you can consider as
breaking. So your voice is breaking. So I'm not able to understand what you are saying. So if you can type it in the chat box, probably.
Yeah, that's good. Yeah.
okay. Okay, I will try to. Okay.
Yeah.
Yeah.
Okay.
Okay. Sorry for that. Yeah.
No, no, it's fine. But yeah, so the voice is breaking. So yeah, so let me just go ahead with this, and then probably at the end, uh, or you can actually type it in the chat box, then I can answer that. Yeah. Yeah, so now let me talk about the in the interacting theory. Okay. So here, of course, basically I will use the relationship, which is basically the soft theorem and asymptotic symmetries. Sorry. Symmetries, I mean, there is a large literature on this, but basically this was essentially, well, I mean, this started with the work of Strominger. Mm, okay, and essentially the statement is that if you have a theory of gravitons or gluons or photons, say, So, okay, so in a theory, containing gravitons, photons, or gluons, the soft theorems, the corresponding soft theorems, can be thought of as word identities it is for asymptotic symmetries or some symmetries. Okay, I mean, well, from our point of view, I mean, the way I will be working, it's not, well, the asymptotic, because I'll not be talking about any kind of bulk here. As for asymptotic, symmetries, and okay, and the second is that this S matrix satisfies these word identities. Okay. Okay, so I'll give you, so this is actually it's a vast here, but I'll give you an example which I hope will clarify this thing. So let me talk about the leading soft graviton theorem.
Shamik, Arindam's question is there in the chat box, so maybe you can read it out and look at it.
Yeah, so maybe, so once I go through this one, this infinite symmetry. Okay, so yeah, so so let me first go through this, then I can actually answer to his question.
Yeah, sure.
Is that fine?
Yeah, sure, sure.
Yeah, okay. Because I think yeah, I have half an hour more, so I just want to finish this part. Please. So leading soft graviton theorem, okay, or the word identity for super translation. Okay, so what is the leading soft graviton theorem? Okay, so what is a soft graviton? Basically it's a graviton with very small energy, or zero. Okay. Energy. So in our notation, so where we wrote this p mu as some omega 1 plus z bar, and 1 and z plus z bar minus I z minus z bar minus z bar. Then soft means you take the limit where omega going to 0. Okay. So now, so basically the question is, suppose you have some scattering amplitude. So this is an S matrix element. So something is happening here, things go out. And now you can have some graviton, which also goes out. Okay, so suppose this is a soft graviton. So this can come out of the any of the legs. Okay, so you have to sum over all of them. And basically the statement is that if you write this S matrix as in this way, so epsilon I omega I and zi bar sigma I, and then let me talk about an outgoing soft graviton. So let me write down the energy of the, okay, I start with the hard A, so this is just omega z bar, and it's a positive helicity soft graviton, say. So this can be expanded. So this amplitude can be expanded in powers of omega, and the expansion basically it starts with a pole in omega, and it looks like the expression is given by minus kappa by 2 1 over omega, and then you have the sum of I epsilon I omega I z bar. So I have actually written everything in terms of this omega and z bar times your S. So you can call it n plus 1. So it's an n plus 1 particle scattering amplitude. And then this is Sn involving only the hard particles. Okay, plus you have higher order terms, like the first one is the omega to the power 0 and okay. So you have a pole term, so this is the omega equal to 0 pole. And now you can see that so this is a soft factor, so this is the soft factor, and this is the S matrix for the n hard particles which you have here. Okay, and so this is essentially a statement of factorization. Okay, the residue is essentially the soft factor times the n particle S matrix. So now we can actually isolate this thing. Okay, so the way we okay, so this kappa here is square root 32 pi g Newton. Okay, and the thing is that in the rest of the discussion, we will take kappa equal to 2, because this kappa by 2, so this will just simplify things. Okay, so now I want to isolate the residue. So I want to extract the residue of this omega equal to 0 pole, and I can do this in this way. So I can write this as limit omega going to 0, omega times S, say n plus 1, epsilon I omega I equal to minus sum over I. So this is sum over all the hard particles, remember? Okay, so in this way, so if you take this, if you perform this, then the rest of the terms are gone. So you are just left with this single term. Okay, so now now we can write this S matrix as, since this is an outgoing graviton, if you write it in this way, so A omega z bar sigma equal to plus 2, and a bunch of A's, and then a bunch of A daggers. Okay, then you can see that you can take this limit inside. So this I can write it as So yeah. Where we have defined this object, which is S plus. So this is the leading soft graviton operator. Omega is taken in, sorry. So this is omega, you multiply this by omega, it is essentially this this thing. Okay, so you get omega times a omega z bar sigma equals plus 2. Okay, so this is called the leading soft graviton. And what we will now see is that this is also the super translation current. Okay, so we will now see that. So in order to see that, it is actually best to go to the spatial sphere. So you can do the marine. So basically, we can write this object as S plus 0 z bar, and then you have a bunch of creation annihilation operators for the hard particles. So this has this form. Okay. So we want to basically get rid of all these omegas. Okay, so I do the Makin transformation, and I also introduce the U. So this becomes S plus 0. So now Makin transform. So this will, I can write it as okay. So this is the form in the, so this is the form of the super translation. So this is essentially, or the not the super translation, but the leading soft graviton theorem. So this is the leading soft graviton theorem in Main space. Okay. Okay, so now we have to do something more actually to get this thing. So what we get is that this, you have this S plus. So now what we can do is the following. So note that the right hand side, so there is a single power of Z bar. Okay, so basically the statement is that note that the RHS is linear in Z bar. Okay, so what we can do is that we can do an expansion like this. We can do an Z bar expansion because it is a linear in Z, and let me write it in this way. Okay, so I write this as P0Z minus Z bar P minus 1Z. So P0Z and P minus 1Z, they do not really depend on Z bar because, well, the right hand side, so there is a single power of Z bar. And so this P0Z and P minus 1Z are currents, and they are correlation functions with a bunch of primaries. Is you can read this out from this soft theorem written in this form. So you can just equate the power, equate the coefficient of Z bar and Z bar to the power 0 on both sides, and what you get is the following thing, that this P minus 1Z times sorry. So P minus 1Z, so that is the coefficient of minus Z bar. So I have to basically equate that. So what I will get is, it's a sum over I, 1 over Z minus Zi, I del Ui, and then this. And you also have the other correlation function, which is essentially the coefficient of Z bar to the power 0. So that has this form. You can the coefficient of Z bar to the power 0 is essentially Z bar I. Okay, so let me call it the word identity 1, and this is, so you can now, you can see, if you just look at these two words, so these have more or less the, well, I mean, this has quite standard form. So you have the pole terms, which is 1 over Z minus Zi, and the residue at the pole will essentially be the global transformations, which are generated by this P minus 1Z. And similarly, okay, so this is something which we know from our experience with the two-dimensional conformal field theory. So here also we have to look at the residue of the pole at Z equal to Zi, and that will essentially give us, tell us that how the global symmetry generated by P0Z is acting on phi. Okay, so let's first look at the word identity. So let's first look at the word identity 1. Okay, so now okay, yeah, so this is the one. Okay, so from 1 it follows that the current. So these are the word identities, like the standard form of word identities in 2D CFT. You can think of the U as something which is just going on for a ride. It follows that the global symmetry generated by P minus 1Z is, I mean, okay, so you just have to look at the residue at the pole. Suppose I want to see that how it is acting on the field phi I. So I just have to look at the residue at the pole at z equal to zi, and that is essentially given by, you can let me call it delta minus 1. So phi epsilon u z z bar. So that is given by some I del u phi epsilon h bar u z z bar. Okay, so that is the residue at the pole. Okay, because I del u is there. And now similarly, the global symmetry generated by P0Z is, so I have to look at the residue. So that is Zi bar times I del Ui. So I can write delta 0 of phi epsilon h bar u z bar as z bar I del u phi epsilon h bar. So these are infinitesimal transformations. If you want, you can actually insert some infinitesimal parameter. Okay, says I. Now, what are these transformations? So these are essentially transformations on the coordinates u z z bar of the form. So this one, this delta minus 1. So this transformation, it's a constant shift in u. Okay. So delta minus 1, this generates u plus some constant, and z z bar, well, z bar remains unchanged. Similarly, delta 0, that generates the transformation u plus some constant into z bar. Okay, and z z bar does not change. Now these are the global space-time translations. So if I go back here, I wrote these down actually. So these are the global transformations. So are u going to u plus a plus bz plus b bar z bar plus c z z bar, and z z bar will not change. So here we have realized, we can see that these delta naught and delta minus 1, they generate the global transformations u going to u plus some constant and b bar z bar. Actually, we will also see that how this bz and czz bar actually will act. Okay, so we have recovered two of the space-time translations in this way. So now you can see that how this is exactly what we expect. But now actually we see that that this is well, I mean, this is quite, yeah, that in the same way as in the in 2 dimension, you can also define an infinite number of other transformations. Okay, now what are those transformations? So for suppose you look at this word identity, this p minus 1z times this, it has this form. So there is a pole in z at z minus zi. So zi is at the points where these primaries are located. And the point is that from here, you can see that, for example, oh, sorry, that this del bar of p minus 1z is actually 0. And similarly, del bar of p0z is 0. So that is the conservation law, right? That is, we know. But then by the standard A, so if these are conserved quantities, I can multiply these by any function of, say, z, or okay, I mean I'm using If then suppose I multiply it by any holomorphic function of z, then that is also conserved because del bar of g is actually 0. Similarly, in this case also, we have some g prime z, p0 z. So that is how we have an infinite number of currents. So we have infinite number of currents. Currents of this form, some function, some holomorphic function times p minus 1z and some other holomorphic function times p0z. Okay, so that's how we can define the modes of this EM. So in particular, what we can be, so this is, so let me just discuss, for example, the way you do. For example, in the 2D CFT, I have this stress tensor. Okay, so you do this mode expansion like this. Okay, so these ln's, so they are like z to the power n plus 1 tz. Okay, so this you can, so this is essentially one of the holomorphic functions, just the way you said that gz, g prime z. So this is one of the basis of holomorphic functions, and you can integrate that, and that gives you the charge. Okay, and then that generates some when acts on some primary operator, it gives you something which you know. Okay, so similarly in this case also, what we can do is that we can define modes. So define modes of p minus 1z and p0z, or the infinite modes, or these are basically the infinite number of charges like the ln's. Okay, and we can simply define them by their action on a field like this. Okay, let me just write this down. Okay, so these are where these n's are integers. So now you can see, so these are the conserved charges, infinite number of conserved charges. Now, what do they generate? So this is the commutator, and you can see from here that you can think of this equivalently as acting on the u, z, and z bar. So you can see that the z bar does not change because it is acting with a del u. Okay, similarly in this case, so what will change is only u, but no z bar. So let me write it, delta n minus 1. So that generates the global transformation. So Pn minus 1 is this z to the power n plus 1. So this is u plus some xi, some small number, z to the power n plus 1, and zz bar remain unchanged. Similarly, delta n comma 0, so that generates the transformation z bar and zz bar do not change. Okay, so now you can see that these are essentially the super translations where now, okay, so this n belongs to z, and the point is that for n equals 0 minus 1. Okay, so if you look at n equal to 0 and minus 1, so these are the global space-time translations. So the okay, so let me be more explicit here. So the generators P minus 1 minus 1, where n is minus 1, P0 minus 1, and P minus 1 comma 0, and P0 comma 0. So these are, so they are generators of 4 global space-time translations. Okay, so that is of course visible from here. So you, so P minus 1 minus 1, so you can see that that generates this transformation since it is z to the power n plus 1. So in minus 1, so u plus some xi, some constant, so that is on P minus 1 0, or okay, say P minus 1 0. So that generates the transformation u going to u plus xi times z bar. ठीक है? Similarly, P0 minus 1 is u going to u plus xi z, and minus 1, yeah, and P0 comma 0, so that gives you u plus xi z z bar. So these you can see are the 4 global space-time translations that you shift u by some constant, then z bar, z, and z z bar, and the rest of the objects, so they are the super translations. So rest of the charges generate super translation. So this is the object that, so you can see that you have infinite number of space-time translations. I mean, well, I mean, you have basically in the interacting theory, you really have an infinite number. So these are the objects, like, so for example, Pmn, so that generates the transformation z to the power n plus 1, z bar to the power n plus 1. So this is, so now if I go back to my earlier this 2-point function example, so this is precisely what I said, that u goes to u plus f z z bar, and then I wrote down that you can make shifts of this form, that u going to u plus some delta is some small number, and z to the power n plus 1, and z bar to the power n plus 1. And these are the basically the basis of functions of this form, say f z z bar. So f z z bar, you can expand it in as a, you can write this as a linear combination of the z to the power n plus 1 and z bar to the power n plus 1 by changing m and n. So this was visible at the level of 2-point function in the free theory on Scri plus. And now we see that if we go to the interacting theory, then this leading soft theorem, that is essentially the word identity for these super translations. Okay. So this is one example, and next time actually we will discuss the subleading soft theorem and what kind of word identity it gives. And then in the other lectures, actually, we'll see that how this can be used to compute some scattering amplitude in 4 dimensions. Okay, so that is so far the goal. Probably, yeah, I need, okay, I have to tell you something about the conformal soft theorem, but that I will probably, yeah, I can do next time. Okay, so this is roughly, I mean, this is essentially the idea. So you start with the soft theorem, you write it on the celestial sphere, and you will see that it always looks like this. So you can always write it as a word identity, and then you can actually get an infinite number of symmetries from there. And then you can actually use them to determine some scattering amplitude, at least some set of scattering amplitude in 4 dimension. So that we'll discuss in the future lectures. Okay. Yeah. So I think I'll stop here. So if there is any question, then you should ask me now.
So there was a Shamik, there was a question in the chat box, but before you go to addressing that question, yeah, but 1 second. So I just wanted to make sure that I've understood the logic behind this. So you started off this lecture by saying that there are these extra symmetries by looking at these free correlators.
Yeah, these 2-point function, right?
Yeah, the 2-point function. And then you constructed the word identities corresponding to these symmetries, right?
Yeah, you can, right, yes. So then we go to the interacting theory, which is essentially the thing that we want to deal with actually. And there actually we use this thing that soft theorem and this correspondence between the soft theorem and the asymptotic symmetries.
But the asymptotic symmetries that you showed us was for the free theory. So why should they still be symmetric? Yeah.
No. So that was so that was a motivation for why one should really, like, why you can basically imagine that the interacting theory can have an infinite dimensional symmetry. So now, because the thing is that although it is there in the free theory, but in the interacting theory, this could be gone, right? But now what we showed is that it is still there in also, it is also there in the interacting theory.
So what do you mean by we showed that it is also there? I mean, you constructed the word identity.
And that we use the soft theorem, and then we then we showed that you can think of the soft theorem, okay, as the word identity for this. So that's what.
Okay.
So this one and this one. So this we got from the soft theorem. And then what I showed is that, okay, so now you can use your standard intuition from the 2-dimensional conformal field theory, and then you can interpret them as these. So first, what I did was that I just looked at the global transformations which are generated by p minus 1z and p0z. Okay, and those turned out to be the global space-time translations of this form. U going to u plus some constant and u going to u plus some constant times z bar. But then then I showed that these word identities imply that this d bar of p minus 1z and d bar of p naught z is 0. So that means essentially that d bar, that this d bar of any function, say any holomorphic function g of z times this is also 0, and that essentially gives us an infinite number of e. And then I showed that if I basically take gz to be some z to the power n plus 1, then I get all these super translations.
Right. Now, I just wanted to clarify this the meaning of this object phi, because phi so far you have constructed in a free theory. But now, if you are talking about phi in an interacting theory, don't you need to talk about an interaction picture or something like that? I mean, Where did
Yeah,
that discuss?
yeah, I think you can do it actually. But the thing is that, well, so my construction of the free theory was essentially was a kind of, I wanted to motivate this thing, and this is also useful because the thing is that the transformation laws of phi and all these things, they of course do not depend on whether it is in the free theory or in the interacting theory.
Right,
Like the
right,
transformation law of a
right.
free scalar field and an interacting
Right,
scalar
right.
field are the same.
Yeah, yeah,
So
yeah, yeah.
in that sense, actually. But then the point is that we basically use this fact that if I do the Mellin transformation of the S matrix, uh, okay, so this object transforms like the correlation function of a conformal field theory.
Yes. Okay.
Okay, and so that essentially told us that, okay, so let's see, imagine that we have these operators in this way. Okay, and you can actually, the point is that these operators are also essentially constructed in the free theory, but the thing is that depending on the value of epsilon, whether it is plus minus one, it has to be like a out or a dagger in.
Right.
So they are like, these are not the same, like these are not the main transformation of the same a dagger actually. So there is a relation between a in and a out, and that is essentially where the interaction goes into. But the thing is that as far as the word identities and these things are concerned, they will not see. I mean, they have this form actually. So I just need a bunch of fields with certain transformation laws. So
Mm,
those are these things.
I see.
Yeah.
Okay. Uh-huh. Yeah. Maybe you can address Arindam's question in the chat box.
Yeah. So let me just look at this thing. There is no reference of metric. Yeah. So we have actually defined it. Well, the theory is defined on Scri plus. So the first thing is that this particular statement that the theory is defined on Scri plus. So that is not required, and also strictly speaking, it is not true because I have not used any kind of bulk in like any kind of bulk picture, or I have not introduced any kind of metric for which you can say that this UZZ bar has a degenerate metric. So I did not need that thing actually. So this, you can just think of this as an abstract three-dimensional space, and the only thing it basically the thing which is required is that the Poincaré group acts on this UZZ bar in the same way as it acts on Scri class. Okay, so that is essentially what I mean by that this theory is defined on Scri class. Okay, I mean not more than that. Now the point is that is that
Okay, but what is holographic statement? What is that some bulk time and which
no,
should
your
be
voice is actually breaking.
do
Yeah, Arindam, your internet connection is probably not good today. So can you just type out your question again in the chat box for the response?
uh,
So probably he is trying to ask that this holography means that I have a bulk space-time and then I have a boundary, and then so you need some scribe. But that is not exact. So what we are doing here is basically, well, we are not really talking about a holographic A because that requires both the bulk and the boundary. But what we are doing here is that I am trying to construct some kind of uh, theory which will which has all. Okay, so the basically we are trying to construct a theory which has all these infinite dimensional symmetries. Okay. So this is not exactly holography, because that will require, of course, a discussion of both the bulk and the boundary. But the point is that, well, it is most likely holographic, because these infinite uh, symmetries that we talk about, so that can also be realized as asymptotic symmetry in flat space.
So hello. So here you are by infinite symmetries. You mean the super translations only, right?
Yes, so far.
But
But
in
next
the
time I'll talk about some more actually.
I see. So would this be the goal to construct theories that has both the super translations and the super rotations as well?
Well, the super rotation, of course, will be constructed in a different way, but we'll well. So yeah, so that we'll talk about next day. But I'll not focus so much on the super rotation, but rather I'll talk about this what is called this acid, which we discussed, this SL2C bar tentative algebra. Okay, which is the same as so this is the one plus the super translation.
But from the point of view of the bulk, the asymptotic symmetric group has both the both the super translations and the super rotations, right?
And also this one,
This one,
yeah,
I see.
this SL2C bar. So that I will discuss in the next lecture actually.
Okay.
So basically, you could have asked the same question, like if somebody asked you, like if you want to construct a theory which has a super rotation as a symmetry, then of course what you will get is a conformal field theory. Now, is that holographic in what sense? Then actually you go back and then you see that if you consider asymptotic like asymptotically ADS3 space-time, then the Virasoro can be realized as the asymptotic symmetry, and that is essentially the statement that the conformal field theory is dual to string theory on asymptotically ADS3 space-time. So basically here what we are trying to do is essentially trying to find out some kind of structure similar to conformal field theory, which has all these infinite dimensional symmetries built in. And then you will see that, and then you can say that all these infinite dimensional symmetries, they can be realized as asymptotic symmetries of flat space-time. And then you can say that, well, so that means this boundary theory which we have constructed is holographically dual to whatever is there in the bulk in asymptotically flat space-time. Okay, so that is kind of the, I mean, that is roughly the thing that we'll do. But I mean, we'll do in the sense, I mean, we'll do a very small, I mean, only a very small, I mean, well, I mean, it is just a corner of this. Yeah. So this is essentially the computation of scattering amplitudes using these things. So that, of course, will be our goal, because the scattering amplitudes are the observables in the asymptotically flat space. So those need to be computed from the dual theory. Okay.
Okay, thank you.
Yeah.
Any other questions? Yeah.
So I just wanted to mention that I have so I have actually written down this in a much clearer form. So it is it will just yeah. So you can actually also have a look at that. It has some.
Right. So this will be in the notes.
Yeah, yeah. So it is already there actually. So.
Yeah. Okay. So maybe I can ask one more question before we
Please go ahead.
So in the second lecture you were you constructed this phi as a Mellin transform of the creation and annihilation operator, right? I mean,
right. Yeah.
That's how you started, and this was, I mean, at least from the discussion point of view, this was in the free theory. But
Yeah.
then this A and A dagger could have been the creation and annihilation operators in the interacting theory as well. I mean,
Yeah, the only thing, yeah, the free theory and interacting theory, the difference is that the A in and A out are the same.
yeah,
Yeah, so that is the only.
yeah. But, my
Otherwise,
question, yeah, that's right. But my question was that when you were when you were getting the algebra of symmetries,
right.
you were using the commutation of H with A,
Yeah,
and that is what gave you the commutation relation of H with phi.
right.
So in the interacting theory, what happens to these commutation relations? Do they remain the same, or do they get modified?
No, they don't. They don't basically change. That's in fact that's what we showed. If I look at the word identities, this P
Ah,
minus 1z and P0z. Okay, so
uh-huh.
this half of H plus P3. Okay, so let me just read this. So this half of H plus P3, say
Hmm.
for example, so that has a simplicity in the sense that shifts U by a constant. So that is the same as P minus 1 minus 1.
Mhm.
So now we know what it is doing in the interacting theory, and it is doing. If I look at the word identity, say okay. So let me just. So this is, I think, yeah. So this is the word identity one. Now I can, if I can construct some kind of Hilbert space picture, just we do in the two-dimensional conformal field theory. So from there, I can still write that this object, that this P minus 1 phi epsilon h bar u z bar is equal to your I del u of phi epsilon h bar u z bar. Or
Okay.
if you don't have the u, you don't want u, or I mean you can also do it that. So you have just phi epsilon h bar z bar, uh, that is equal to your epsilon times your phi of epsilon h plus half
Yeah.
h bar plus half z. Yeah.
Okay. But
So
in the
yeah.
notation of the A and A dagger, does it mean that the commutation of H with A is equal to minus epsilon P0A, the one that you were using earlier for the free theory?
Yeah, actually it is the same actually, because this P minus 1 minus 1. So I think there is a sign here. It is
Yeah,
this
yeah,
minus P minus 1 is the same as half H plus P3.
okay. So the proper statement, just so that
Yeah.
I clarify, is that the total Hamiltonian, the interacting Hamiltonian commutation with the interacting creation on
Well,
annihilation
so
operator is
in this
proportional
case,
to. Uh,
yeah, so in this case, these Hamiltonians are kind of the asymptotic, yeah, right? I mean, they are acting on the free, like
Asymptotic.
as the asymptotic states actually.
Mhm.
And basically, whatever is there in the interacting theory, so it is all there in these two word identities, this P minus 1z and P0z, and that is essentially the statement. So this you should take as the full specification of this super translation, which
Yeah.
includes all the global space-time translation
Yeah.
for the to the interacting case actually.
Yeah. Yes,
So
yes, somehow. I mean, so there's this in axiomatic quantum field theory. There's this theorem called Hagg's theorem, which questions the existence of the interacting picture. So somehow when you're defining all this, you're bypassing all the subtleties related to that. So I'm just wondering where those subtleties were buried.
well, this interaction picture. So is this the statement that the interaction picture does not exist?
Yeah, yeah, yeah.
Yeah, so that of course I have not really, but the point is that, well, we don't really need to go to the interaction picture. We can just work with the A in, A out. Now the interaction picture, of course, will come if there is if I talk about an interpolating field which goes between the in and the out and do
Mhm.
all these things. But in the like the thing that we are doing I don't think we will really need that thing.
Mm.
Because suppose, so I just talked about the free theory just to motivate a, that was the first year. Second thing was that the transformation laws of the fields, they don't, of course, they don't depend on whether the theory is interacting or free. So that's a good thing. But the point is that basically, if I start, if I do it completely axiomatically, okay, then I will start with the word identities 1 and 2. So that's what we do in the 2D conformal field theory, right?
Mm.
And then I will just define these phi's, and some of the phi's are basically phi in, and some of the phi's are phi out. But I don't need to define any kind of interpolating field,
You're right.
because that lives in the bulk, and we don't really need that.
Right. I see.
So, okay, so let me just, since I mean, this is an extremely important point actually. So since you said this, let me just make this statement that axiomatically just, you just start with the soft theorems.
Mm.
Start with soft theorems plus the Main transformation. And this, of course, does not require any kind of interpolating field theory, and that's all you need actually.
Mm. I see. Yes. Okay.
Yeah, so I think this Hague theorem
Yes.
is not playing any role so far in this, because I mean, we basically have some phi out and phi in, some something like that. I mean, and that's all we need actually. So here, of course, it is implied depending on the this index epsilon. So epsilon I equal to +1 means it's an outgoing field. Epsilon I equal to -1 means it's an incoming field. And I don't need to really need, I don't really need an interpolating field, because
Okay.
these the- these word identities are all I need actually.
Yeah. Okay. Very good. Yeah. Okay.
Yeah, yeah. I mean, that's a very important point actually, because when I compute the scattering amplitudes, so that will, I think that does not really need any kind of interpolating field
Okay. Yeah.
interaction picture. Yeah.
Yeah. That's good. That's good. So it's basically this is the statement that your symmetries are constraining your.
Yes, yes. At least in some very special cases, but it's an infinite class of infinite number of scattering amplitude, and here we don't read any kind of interpolating bulk fields actually.
Okay. Very good.
Yeah. So yeah, so that's a good point. So somehow this does not. So this basically says, yeah, I mean, you don't really care about Hugg's theorem, I think, in this context so far. Yeah.
Okay. Okay, thanks, Shamik. So we will reconvene next week on Tuesday. I will just confirm the time.
Yeah, sure.
Yeah. Okay. Thank you very much.
Great. Yeah.